Okay, all right, let's get started. So with that, let's do a recap of what we covered last time. Right, so last time we talked about probability or random variables. And we said there's two kinds of random variables. The first one we covered is the discrete. So for discrete distributions, then we have two vectors, right? So we have a probability vector, P1, Pk. And we have the values. So let's say W1 to Wk. Okay, so for each value, we associate probability. So the thing to remember about this kind of random variables for both discrete and continuous, actually, right? So be careful about where you're computing. Okay, so for example, one question in the homework, okay, says, let's say Wi are the wind speed. Okay, let's say these are the wind speed. Each with probability Pi. Okay, so I have some wind speed, either each have a distinct probability. Then a question that we can ask is, what is the average wind power? Okay, so let's assume we have 100% efficiency. And let's ask, given these are the possible speeds, what is the possible power? What is the average power we can produce? So the important thing for this kind of problems is to do the following, right? So the average power is the sum of the probability, where you cube each of them individually. Okay, where you cube each of them individually. All right. So each one of them, or so the average power, this is proportional to Pi Wi to the Q, multiplied by some area and density and 1/2, things like that. Okay, so the important thing is you cube the values first, then you multiply by the probability, then you add them up. Okay, then you add them up. This is not, okay, it's not, you compute the average speed. Okay, all right, so this is wrong. Okay, so averaging, then cubing is wrong. Okay, so the average power, okay, so average power, you have to be cubed first and multiply by probability. Okay, this is not the power of the averaged speeds. Okay, these are different things, right? So if we want to find the average power, you must find the average, you must find the power for each individual speed, then multiply by the probability, then sum them up. Okay, so in that homework question, for example, you cannot compute the average speed first, then cube it and say that's the average power. Okay, so it matters when you multiply by the probability and when you apply the function, for example, from speed to power. Okay, so just be mindful. We're computing the average of some quantity. You have to compute the quantity first, then averaging. Any question about this? Okay, so the order matters. So the order matters. Right, so the order, again, so the order is very important actually to this kind of calculations, right? You can almost never switch the order when you compute things. Right, so this is something to pay attention to. It's very common to say, compute the average speed, then compute power just based on that. That's incorrect. Okay, that's incorrect. Okay. So another thing we look at is we said, okay, we have the continuous distributions. We have continuous, and this is what we call as the probability density function. Okay, so this is some function that's of a continuous variable. Okay, so last time we said, for example, that we have Gaussian or normal random variable. So for normal random variables, what we have is a two parameter random variable, right? Has two. It's parameterized by the mean and the sigma. So this is, so for Gaussian, we have 1 through pi sigma e to the x minus the average value squared 2 sigma squared. Right? So this is Gaussian. This is our Gaussian random variable. So the issue with that last time is Gaussian is there's two problems, right? One, it's symmetric. Okay, symmetric around its mean. Second, this X has infinite support, which means that for a negative, for example, for negative values of X, the probability is non-zero, or of W. Actually, so let me be more consistent. Okay. So this is symmetric, okay, which makes the calculation often very easy, but may in real life, wind speed or wind power or any of those functions you care about is probably not symmetric around its mean. And this has infinite support. So what infinite support means, for a very negative W, you still have some positive probability of this occurring. Okay, so even if the W is very negative, the probability may be positive, which again, of course, not realistic, right? So we're talking about something like speed or power. Now, of course, it can only take on positive values, right? So cannot take on negative values. So we want to rule out, right? We want some distribution that rules out these, there's two features, right? It does not have these two features. Okay. So any questions up to this point? All right, so one thing we can do, right? So what we can look at is something called a chi-squared distribution or Rayleigh distribution. So this distribution really is basically saying I want a distribution that only covers the positive ranges. Okay, so I want something that only takes on positive values, that maybe is not symmetric and doesn't go, that's not symmetric and doesn't go beyond zero, right? Doesn't take on negative values. So the distribution function is something like this. Okay, so this is where we take, now W is assumed to be larger or equal to zero. Okay, so the chance, right? So the function is only positive when the argument is non-negative. And this is the sort of function we get. Over its mean squared e to the minus pi over 4 W over this average square. Okay. So it happens to take this kind of parametric form. Okay. So this is a single parameter. This is just one parameter. This is the average value of W of this random variable. So this average value and only take on this. So instead of having a mean and instead of having both mean and variance, this thing only has a mean. Okay, only has a mean value. So what you should look at is, so okay. For negative values of W, we simply say the probability is zero or the density is zero. There's no chance of this thing occurring. Okay. So if you plot the function, it will look something like this. Okay? It will look something like this. Basically, as a still a single peak, right? There's only one peak of this function, but it's not symmetric around this peak, and it only takes on positive values. Okay? So that's the function we have. Right. So if you look at this sort of function, actually it's a lot of parameters like pi over 2 and the square of the average. These are used to make sure we integrate this thing out to be 1. So a lot of parameters in this kind of functions as to make sure this kind of integral is 1. Right? So this has to be 1. When you integrate entire density, right? This means what is the probability of a right? This is integrate all the possibilities, right? So this is probability of any of the possibility happens as 1. Something has to happen. So that's why you see all this kind of parameters, pi over 2 and things like that. Right? So sometimes maybe a little bit strange why there's so many pi's and things like that. It's just because this integral needs to come out to be 1 to the normalizing constant. Right? So we have some sort of constant that pops out. Okay? For this. Any questions about this? Okay, so this is not used as often as Gaussian, for sure. It's not used as often as Gaussian, but it is fairly common in the wind speed. Okay, this is quite common for wind speed, because again, wind speed can only take on a positive value, right? So this is a distribution that covers a positive value. And still having a single peak makes sense. So this thing has a single peak, right? So this is what turns out to be. Does anybody know what else this thing describes? For the folks who has maybe taken something like wireless communication. Okay, so if you look at something like wireless communication, often you describe a channel strength using this sort of chi-square distribution. Okay, so this basically says there's a sort of peak in the middle and falls off quite fast. Okay, so this is often used to say, if you communicate to your cell tower, your signal strength is something like this. Okay, so there may be some place you get a strong signal, then the signal falls off quite quickly. Okay, so this sort of chi-square still has the property that it drops off very, very quickly. Okay, so it tends to drop off very, very quickly as you go. All right, so this is a distribution, so there's many things we can compute from it. For example, right, we may want the variance out of this thing. So unlike the Gaussian distribution, you cannot directly read off the variance anymore. Okay, there's no variance term in this, right? It's only characterized by the mean. So we need to compute the variance, and right, so basically compute the variance, do an integral like this. So you're not expected to do any integral of this form. Okay, you're not expected to do this kind of integrals, but it's good to, just a reminder, you can compute all this kind of statistics from the distribution. Okay, so this is one statistics. Now, of course, we can compute the probability. This is larger than some number. Okay, so this, for example, probability is larger than a certain number, WA. Okay. So there's a bunch of other things you can compute. Right? So given statistics, we can compute all these numbers. Okay, so any questions about this? Okay, so this is just repeating the statistics, right? You can remember, if you see a homework question, you can look up here. or something like Wikipedia will have all these formulas for you to use. Okay, so you can look up this kind of statistics on the internet if you need it. So the advantage, the nice thing about the Rayleigh distribution is, again, only depend on a single parameter, right? Only depend on the mean or the average. Right, so this only depend on the average. So empirically, I can measure this average very easily. Right? So remember, we can collect a bunch of samples and compute the average very easily. Right? So this is easy to measure. Okay, right? The speed or power, if you want to measure this quantity, that's easy to measure. The density is easy to use. Okay? So it turns out having a density of this form makes a lot of integrals easy to do. Okay, so this may or may not matter when you're using a computer, right? But when you're doing a lot of analysis that requires a closed form solution, so this type of, so sometimes you may need a closed form solution. So maybe useful to have a closed form solution. And this kind of density really makes a closed form solution easy to get. Okay, so the nice thing is I have a W multiplied by e to something W squared. Okay, so remember doing integrals, these are the nice integrals, right? These are the nice integrals we have. Okay, so now if it's unlikely you run into this, but in research, sometimes you really need a closed form formula, and this will give you a closed form formula. Okay, just right. So it's easy to use, it's easy to measure, it's easy to use if you ever need to do this integration by hand. So you still do see this kind of model happen in practice. Okay, you still do see this happen. Right? So let's do an example. Right? Let's do an example of how do we use this kind of probability models. Right? So this example says I have one turbine that's basically produces 150 kilowatts of power and has a diameter. The blade has a diameter of 48 meters. It has a 50-meter power. Then the average upwind speed is 5 meters per second at 10-meter height. Okay? And the total efficiency, right? Total efficiency is 30%. And in front of that, let's assume I have a friction coefficient. Okay? So let's assume, I have some efficiency both from CP and this you can think of as a gearbox efficiency. Okay, gearbox efficiency. So I assume these are my efficiencies. Okay, and then so let's think about what is the annual energy I can produce, assuming this has the chi-square or Rayleigh statistics. Okay, so before in the homework, a lot of things we computed is basically saying, given one wind speed and something else, let's find the current power production or find the energy production, assuming this wind turbine runs for this long time. So now we're gonna say, let's assume things are random, right? Characterized by this statistics, by this particular distribution. And let's say if things are random, right, how much energy do I produce per year? Okay, let's assume things are random, how much energy do I produce here? Right, so the randomness, so here you can think of this is a rating. Okay, so these are the rating of the turbines. So it doesn't mean the turbine is always operating at 750 kilowatt. Right? So the turbine is rated at 750 kilowatt. Okay? And the randomness comes from wind speed. So the randomness comes from wind speed, right? So what this randomness comes from wind speed. And what do I mean by this question? Okay. This is the alpha in for the height equation. Sorry, my mistake. This is not the gearbox efficiency. This is alpha for the wind speed and height equation. So this is that alpha. So basically what we know is I have a 10-meter height. My average wind speed is 5 meters per second, right? But my turbine is at 50 meters high with a tower. I want to know what is the average energy I can produce over the year. I want to know this. All right, so let's look at this problem. Okay, so this is the wind speed at 10 meters has 5 meters per second average. So the first thing we need to do is to compute W average, the average wind speed at 50 meters. Right, so we measure 10 meters high. We have 5 meters per second average speed. So I need to know what the average speed is at the hop height. Okay, at the hop height of 50 meters. So our equation we use is, if you recall, we have at the reference this sort of equation, right? As you scale higher and higher, your wind speed gets scaled through a power law with a coefficient alpha, with this coefficient alpha. So here we have the average speed. We don't know at 50 meters, but we know this is 5 meters per second at 10 meters. 0.2. Okay. So this is our way of computing what the average speed is at 10 meters, at 50 meters. So we get this is 6.9 meters per second. Any questions? Here's something in the audience. Questions? Okay, all right. So this is the average speed. Right. So then if you look at the distribution, so this distribution, if you recall, we get now is pi over 2 6.9 squared e to the minus pi over 4 6.9 squared. Okay. So this is the distribution we have, right? So now we have a turbine with a speed at this distribution, okay, without this. And we want to compute the energy it generates over a year. Okay, so we're sort of quite a few steps away from that, right? We need to compute the energy it generates. Okay, so let's keep going with this, right? So let's compute the, right? So this is so the average speed. So now we need to compute the power. Okay, so now we need to compute the power of this thing, right? So we need to compute the average power. So the average power, if you recall, this is 1/2, or power at the particular speed is 1/2 delta A omega cubed. Okay. So remember what we said at the beginning of the class, you cannot take the speed average and just cube it. Okay, so that's not correct. That's not correct. We have to cube each individual speed and then take the average. Okay, you cannot first take the average then cube it, right? So what happens here is we want to compute the average. what we have is, this is now the average, is now the integral, right? From there to infinity of P times the density function. So this is 0 to infinity, 1/2 delta A cubed pi over 2 squared e to the pi over 4 squared dw. Okay, so this is the computation we'll have to work with, computation we'll have to work with. So if you look at this kind of integral, so basically we'll not ask you to integrate this, okay, in your homework, in your exams. If you ever face with this kind of integral, we'll give you enough to be able to solve this integral. So you would not need to integrate, for example, using integration by parts or things like that. Right? So we'll either directly give you the numerical value, or we'll tell you enough such that you can compute the integral. But the nice things with this sort of Rayleigh distribution, what I mean is you can get closed form formulas, as you can actually get a closed form formula out of this. You can actually get it out of this. So what you get is, if you do all this kind of things, if you do all this kind of thing, this is actually 1/2 delta A, these are constants. 6 over pi, the cube of the average speed. Okay, so this is just by virtue of the Rayleigh distribution being nice to work with. Okay, so just make, you can't, so if you actually went and did integration by parts, you would have found this answer. Right, so we are not going to do it here, but you know, something to remember that this is doable. This is, you can find an answer this way. All right, so then if we have something like this, we're almost done, right? So this, what we need is the output power. The average output power is the coefficient of performance multiplied by the average wind power I have. So we can multiply all these things together. This is 0.3 times 1/2 delta. The area, remember we had something pi 48 by 2 squared. It's 48 in diameter, so 48 by 2 squared here. 6 over pi, 6.9 cube, something like this. And assume delta is 1. You put all this together, we have 170 kilowatt. Okay. So the average output of the turbine after this integral and putting in the area information, we get is 170 kilowatts. Okay. So what about NU energy? Now how do I compute energy? I got power, right? So this is my, on average, the output power of the turbine. Now how do I compute how much energy this thing is generating? Any ideas?
Is it just the average power times the number of seconds in a year?
Right, so you can multiply by seconds. Having things in joules is not, right? So our normal unit is not things in joules, right? So you multiply, very close, but energy is just multiply by hour. Okay, so take this. How many hours are in a year is 760. So what we get is 1.5 gigawatt hour. Okay. So normally when you ask for things like energy in a year, that's given in hours. Okay. So it's giving something hour, right? So that's the idea for a year. Very, very rare do we see things in joules. Quite rarely do we have things in joules. Right? But that's right. Okay, so A760, you'll see this a lot, right? Just number of hours in a non-leap year, I guess, right? So that's the number of hours we have. So This is a fairly typical question you'll see, right? The only hard part is this integral. So in your homework, you don't have to do this integral by hand. But any other questions about this type of question, this kind of calculation? Okay, right. So if you look at something like this, right? So here we are able to get a closed form formula, right? We're able to get a closed form formula. We know the average power, wind power, as this coefficient something times the cubic of the wind speed, right? This is our formula. So why would this kind of closed form formula be useful? Right. So I said sometimes having a closed form formula is useful. Why would having this be useful? Right? What's the difference between being able to have a formula like this versus just chucking this into the computer? The computer will do this integral fine. The computer has no problem doing this integral, no matter you can do it by hand or not. We'll do one-dimensional integrals, and it will give you a very accurate answer. So why might we sometimes want this kind of closed form formula? Any ideas? So if you're an engineer, do you see ever a case for having this as useful? Right. So one reason we may have this kind of formula is that this formula gives you a good idea about the sensitivity. Right. So you have a formula like this. You can easily answer the question of if I increase the wind speed by 5%, how much more power do I get? If I increase the wind speed by 20%, how much power do I get? Okay, this kind of formula allows you to answer this kind of sensitivity questions, right? What if I'm off by 10%, what do I get? Or if you just put everything into the computer, let him integrate for you, then you can do it, but every time you have to redo an integral, right? You have to just reintegrate everything. You have to, you don't have a sense. This is actually still a cube relationship, right? If you blindly put this in your computer, you don't know whether it's still cube. Is it square? Is it cube? Is it to something else? Right? So that's if you have a closed form formula, it makes identifying relationships easier, making looking at sensitivities easier. Okay. This is really not for getting the final answer. Getting the final answer, computer will do it for you. But if you want to know the relationship, get a feeling of is it still cubic? What is the coefficient in front? This is where getting an answer would be having closed form formula is helpful. Okay. So even though you may think nowadays computer will solve everything, there's still use being able to integrate things like this. And again, really is one of the few cases where you can actually integrate it out by hand. So that's why sometimes you see this. Okay. Any questions about this? Okay, so we're going to look at one more distribution. Again, not the Weibull distribution, right? So we're going to only look at three: Gaussian, Rayleigh, and Weibull. So these are the three most common ones. And if you look at literature, these are all used. Right? So we'll cover all of them. If the distribution seems complicated, don't worry about it. Just know this is some distribution and what matters for this kind of distribution. So really, it was a nice distribution, right? But in some sense, it was too simple. There's only one parameter to play around, and the single parameter is the average, right? But often when you look at two, let's say one side, they may have the same average, but still very different characteristics. And so often it's not enough just having an entire distribution characterized by an average number. And that's often not enough. So what is, so sometimes we want more freedom, right? So Weibull distribution, the example distribution with more freedom. It basically has so-called two parameters. This is two parameter distribution. And the two parameters are called, one is a scale parameter C, one is called the shape parameter K. right? So these are just the names we assign to them, right? So we assign these names because, again, we don't have, these are not the mean and the variances. We don't have sort of very clear interpretations of what they are. So we just give them some names. So the skill distribution, for example, is, right? So the skill parameters for this is, oh man, there are some. Okay, so there are some bugs on converting this to PDF. So I'll try to draw the best I can. I'll put up the better graphics later when I post the slides. So here I'll draw it the best I can. Okay, so let's look at the shape parameter K. So why is K called a shape parameter? So basically what K does is the following. Right? So again, this variable assumes, so W is larger than 0, the argument is larger than 0. So what the shape parameter does, so let's say C is 1, is for a small k, for small k, it really doesn't have a peak in the middle. Sort of peak at the highest point is 0 and just decays afterwards. This is for a small k. Whereas for a large k, this is a large k. For a large k has a peak in the middle. Okay, so this is the reason it's called a shape. This parameter determines the shape of the distribution. This is the shape of distribution. So it's called a shape parameter. Right? So when you fit from your data, from your histogram, you can look at whether there is a peak or things just 0 most of the time, just decays from there. So there's more flexibility to control whether you have a peak or not. Versus Gaussian, you have to have a peak. Really, you have to have a peak. Okay? Here, you may or may not have a peak. Right? So it's more powerful in the sense that it's still the same function. Just by changing the parameters, you can get different shapes to come up. Okay? So this I'll replace by a better graphic. And the scale parameter just controls how spread out this thing is. So this is k equals to 2. So this is scale parameter, for example, this is small c. So that's where the shape is concentrated around this peak versus a large C, where things are very spread out. Okay, where things are very spread out. So these are the different what the different parameters does, what they do. Okay, so right, so this is just the idea. So the idea is just to say I want two parameters where give me a flexibility of controlling both how wide the spread is and what the shape is. So contrast this to Gaussian. But for Gaussian, the sigma parameter controls how widespread how wide the spread is. But you cannot really change the shape. It's always a bell curve shape. Whereas for the Weibull distribution, you can control both the shape and the scale. Okay, so that's why people say this is more flexible. Okay, so it's still two parameters. I still only need to look at two parameters, but I can get a wider range of functions this way. Right, so let's look at some statistics we can compute from it. For example, what the mean is, right? We want to know what the mean is. So the mean here is, right? So the bad thing here, if you look at the mean, this is really not something we can do by hand. Okay, so this is, so you look at what the mean is. This is, for example, one where you take k to be 1, c to be 1. And even here, it's just some integral. It's not like we can integrate, what this is, right? So this the integral, we don't know what this integral is. Or this integral actually, you replace the, so you make this identification where x is w over c to the power k, and this integral you have left over. What this is so-called gamma function. The so-called gamma function. Basically, we invent a term for this integral. It does pop up quite often. So we invent a term for this called the gamma function. For you, just remember it's some value. Okay, there's no need to go into more detail with the gamma function. But suffice to say something that this you have to evaluate using a computer. There's no elementary functions for this. Okay. So whenever you see this in the homework, in the exam, we'll just give you the value for the average. Okay. So if you're interested in more, you can look up the gamma function. It's a quite interesting function. But for those, most people who don't care what this function is, just think of there is some average that can be computed, right? But it's not simple anymore. Okay, so where it's here, you can see the trade-off between the probability being more flexible, right, being able to model more phenomena, versus the integral just being hard to deal with. Right? So in Gaussian, we can compute the mean. In Rayleigh, we can compute the mean very easily. Where here, as the mean depends on the two parameters, quite complicated. Okay, so quite complicated dependence. So what this says is also that constructing an empirical distribution is not so easy. Okay, constructing empirical distribution is not so easy because empirically, if this is wind speed, right, what we can measure is I can measure the average wind speed. Empirically, these are the easy things to measure, but that's not K and C, right? So empirically, it's not easy, straightforward to measure K and C. So if you want to use this kind of distribution, then how do you convert, from the data you measure, which is just speed, to the parameter of the distribution, which is the sort of scale and shape parameters? That's sort of more convoluted or more complicated to get. Okay. So this is just, for you guys, just remember this is some function dependent on K and C. Function dependence may be complicated. So if I give you a bunch of data, converting to this distribution is hard, whereas converting to the other two is much, much easier. It's much, much easier to go from data to distribution for the other classes. This is harder, right? Harder to do. All right, so any questions for this? Okay, so let's take a break now because I need to end a little bit earlier at 2 to meet with the colloquium speaker today. So let's take a break now. We'll come back at 1:24, then we'll stop at 2 p.m. today. Okay, thanks, guys. So break now. Any question about homework? I can answer them now. We'll continue the class at 1:24.
May I please ask a question about the homework?
Sure, go ahead.
Okay, so for number 5, for the problem that is similar to it that you did in class, it includes an efficiency term for the turbine. But in the homework, it doesn't say anything about the turbine's efficiency. So should we assume the turbine is 100% efficient?
Right, okay, so yeah, so you can assume it's 100%, just say that. Or if you look it up from the graph, just say you look from the graph. I'll take both answers.
Okay, because I have 2 terms for efficiency. Right. One I got from the graph, and then one is like for a specific wind turbine. So I just use the number that you used in class. But
right, yeah. If you use that in class, that's fine. Or use some other number, just say what that number is for, then it's fine. So use 100%, you don't need to change it.
Okay, awesome. Thank you.
Okay, so let's get started again. So turns out there's some things we can compute easily with a Weibull distribution, right? And the things we can compute with it is the Cdf function. It turns out the Cdf function has an easy form, right? So we can integrate that fairly easily. Okay. So what the Cdf function allows us to answer some type of question saying for how many hours of a year is the wind speed greater or greater than some number or smaller than some number. Right, so for example, let's look at a question like this. Right, so so at a wind site, so somehow we got these. We got enough data to fit that a Weibull function represents the wind speed and has two parameters: c equals 5, k is 1.2. Then we want to compute the number of hours per year when wind speed is 4 meters per second or higher. Okay, so this is what we want to compute. Right? So if you look at this, we're basically gonna use this equation. Okay? So the probability of the wind speed is larger or equal to 4. This is given by e to the minus 4 over c to the k, or e to the minus 4 over 5 to the 1/2, and we get 0.485. So a little bit less than half the time. The number of hours per year this is 4.485 times, again, number of hours in 1 year. Okay. So a little bit less than half the time, we have wind speed or larger than 4 meters or greater. So this is one example how we use this kind of distribution, right? So again, when you in engineering applications, knowing the scale and the shape parameters, often that's not the things you're interested in at the end, right? At the end, the things you're interested in is something like this, right? How often is the wind blowing, or for how many hours do I get, above some threshold, right? So, but then these sort of more interesting questions can be computed if you know the parameter that describes the distribution. Okay. So there's a way to fit this. We'll not cover this in this class. They're not terribly interesting, and this is really the computer is doing for you nowadays. So we can compute this. We can look at the gamma function. We can back this out of the gamma function, things like that. But that's really sort of less interesting than some other things. But we won't cover this in this class. Just remember that if you need fitting, there's enough statistical packages that will fit it for you. You can just get the data point and the package will fit it for you. Right? So if we look at the three things we covered, right? So Weibull is the most accurate. Normal is in some sense the least accurate, but the easiest to use. Really is easiest to use, and which one you use depending on the particular site, right? So you need to take some measurement and figure out which one to use. Okay? So different site may have different, may have so each of these functions may be the best one compared to the site you use, compared to which site we're using. Okay, so this is for a single wind site, right? So this is all this is a single turbine or single site. This is a single turbine. What we care about is, right, so nowadays, if you look at the problem, single turbine is not really a challenge anymore. If you have collect enough data, sometimes you don't even need a closed form description of you don't need a description anymore. right? So if you remember, if you went to this morning's talk, you hear this sort of scenario-based approach. As often we'll just throw all the data into a optimization problem and let it run. So single turbine is not a challenge anymore. But the challenge nowadays really comes down to what to do with multiple turbines. Or multiple sites, right? This is much more challenging. Okay? This is much, much more challenging than a single turbine. So why is this, right? So why is having multiple turbines more challenging? The reason having multiple turbines be more challenging is it's not a single, you don't have a single function describing anymore, right? So you cannot just worry about for one turbine, how likely it's going to produce some value. Now you have to worry about, correlations. Okay? You have to worry about correlations. So that becomes much harder to deal with. We have to worry about correlations. Right? So correlations means I have two or more random variables, right? So if we recall for one variable to describe, right? So for one variable, when we said, okay, I need to describe a random variable, I need a probability and a value can take. Okay, I need a probability and a value. So for two random variables, how do I describe it? Right, so let's say instead of one of them, I have two. So let's say I have Wx and Wy. Right? I have two sites, Wx and Wy. Now, how do I describe them? How do I think about Wx and Wy now? I have two of them. For each one of them, I have a vector of probabilities and a vector of the outcomes or the values that W can take. Now, for two of them, what do you think the description is? Okay, so for one of them, I have a vector. So for two of them, what do I have? Right. So for two of them, what really have is I have a table. Right? I have a matrix table. Right. So what happens is, right? So let's say Wx can take on values Wx1, Wx2, Wx as m. Okay, I have m of these values can take. Wy can take on values Wy1, Wy2. Let's say Wy. So let's say this is capital M, and let's say this capital K. Okay. So there's m possible values. Capital M values this can take. The capital K values Wy can take. Okay. Then how do I assign probability? Right? How do I assign probability? Then for each Wx m Wyk pair, I assign probability PMK. Okay. This is how I assign probability. Right? For any of the pair of values that is possible, assign some probability of this thing. Okay. I assign some probability of this thing. Okay. So, right, so then the requirement So this has to be larger or equal to 0. Then the summation of m, summation over k, the double summation needs to be 1. Right? So these are the possibilities you can take. Right? So if we have two one side, for example, now one can have one speed 5 meters per second, 10 meters per second. The other one can have one speed 4 meters per second, 8 meters per second. I need to assign 4 probability to the 4 combinations. Okay, so this is just we have 2 random variables. Okay. You have this kind of probability, right? This kind of probability. You cannot assign each one of them individually anymore, right? Because these two may be correlated. For example, I have 2 turbines close to each other. Then when one of these turbines has high wind speed, it's likely the other turbines will also have high speed. Okay, right? So that's why you cannot think of each of them individually. You got to think of all this together. You got to all think of this together. Okay. Right. So this is for 2 random variables. So I now have a double indexing. Right. I assign each probability to each of the pairs. Okay. So for 3, I have a triple. Right, then I need to assign probability for that, each of those combinations. So in practice, it's not uncommon for a farm to have 100 turbines. And basically, I need a 100-dimensional thing, basically, to talk about probability. That is exponentially more complicated than looking at each turbine one at a time. So the real challenge today, nowadays, we face is not what happens to each individual turbine. That can be characterized very easily. The challenge is I have a farm with 100 turbines on it. I need to understand this sort of joint probability, right? It's not for each individual one anymore. It's for joint probability, and this becomes very difficult. This becomes quite challenging to compute. Okay? This becomes quite challenging to compute. Any questions? Any about the idea of correlations or sort of joint random variables? Okay. So we will look at we'll look at only 2 variables at most, and we'll only look at something special called the correlation or cross correlation between them. So that's sort of a special thing we'll look at. Any questions?
So is that how do you do more than 2 random variables?
Oh, you just have 3, right? So for example, you have 3, then you basically have a x, so wx, wy, wz pair. So you assign a probability to all 3 of them.
Mm-hmm. And so would you do the same thing if you had 100?
Yeah, so 100, you have to have 100. So it's described the same way.
Thank you.
Yeah, it becomes very unwieldy to use. It becomes very hard to use when you have 100. But in principle, it's described by this high dimensional joint probability, right? So it's a joint probability when you describe everything together. All right, so then this is so we need a shorthand. So let me introduce a shorthand for this. Because often we are too lazy to write out this kind of sums, especially when we have more than 2. Writing out function is hard. So there's a shorthand for this. So what the shorthand is for is following. So we often write something like this. Expectation of some function gx of y. We'll often write this. This is because we're lazy to write out this formula. So we're being lazy here. What we really mean by this kind of formula is this. The sum over all m is sum over all k, g of wx, wy. So this is, we often see a shorthand form where you think there is the expectation of some function. Okay, so this is the short form we'll use. Okay, we'll only look at one example of this, namely being the cross correlation. But that's a useful shorthand for us to have. So I think that's the question set is, when you have 2, this is complicated. When you have 100, it's really, really complicated. And when you have 101 turbines, nobody is going to look at the entire joint distribution. Okay, nobody will look at this 100-dimensional thing. Okay, so what we'll look at most often in practice is something called cross-correlation. Okay, so cross-correlation is simply a measure of how related two random variables are. Okay, so how to relate random variables, right? So the answer to is something like this, right? So again, if you have one speed or one speed at two different sites, a question we may want to answer is if is large, okay, so we may want to answer some question like this. Okay, this is often an important question we ask in power system operations. Okay, we often ask for this kind of question in power system operations, right? So we care about, when one is large, is the other one large or small? Right? So why may we care about this in power system operations if you operate it? Why do you care about the relationship between two things? Why is it not enough to know, X is large, and why do we worry about how related they are? Right? So if your system, yeah, go ahead.
Because we want them both to do well, and so the only way to have them both do well is to know the relationship between them.
Close, right? So the idea from operator is, so as an operator, what do you care about, right? Operator, you care about how much power I have in my total system. So I have if I have two sides, say let's say they go up and down together. What that may create is very large heights, right? So they're both large. Let's say they're very close to each other. So if both has a lot of power, you get a lot of power. If however, if both has no power, then you get no power from both of them. Okay? So you worry about this kind of large swings, right? This may create much larger swings in your system. Compared with, let's say you have two sides, that's anti-correlated. So when one is large, the other one is small, and vice versa. Then what you see in total is the sum power is relatively flat. And that's sort of a different case the operator has to think about compared to two sides that go up and down together. In both these cases, you may have exactly the same average, because the average may be exactly the same. However, the correlation tells you sort of what their relationship is. And based on whether they're very correlated to each other or they're very anti-correlated to each other, you will have different operation problems to think about. You'll have different operation problems to think about. So sometimes the bad news for wind, different wind turbines or wind farms tend to be correlated with each other, tend to be quite correlated, which makes sense, right? Wind is driven by big weather systems. So you have high wind speeds one place, you likely to have higher wind speed some other place. Okay? But that can make operation challenging. Okay? That can make the operation very challenging. You may have a lot of wind, or you may have very little wind, right? Which is not right. So if they're all acting independently, you may think, oh, sometimes things cancel out. But for wind, things typically don't cancel out. They go up and down together for wind. But then if you think about, so what do you think is anti-correlated with wind? If wind goes up and down together, what is trending differently compared to wind?
Solar, possibly?
Solar, right? So solar tends to be quite anti-correlated with wind. So most often, if we have high wind, we'll not have very much solar. Whereas if we have a lot of solar, we're probably not going to have quite a lot of wind. This is particularly if we consider the night and day behavior. Solar and wind are really, really anti-correlated if you take time into account. Okay, so when you have bright, sunny afternoons, relatively little wind, have very windy, at nighttime, you have no solar. Right? So solar and wind are anti-correlated, and you often hear people say they're complementary to each other, which is just a less technical way of saying the cross correlation is negative. Okay, so that's what the idea is, right? So, but the correlation is important. The whole thing is correlation is important. Right? We need to know we have multiple things how related they are to each other. How related they are to each other. Okay? That's the idea we need. Right? That's really the hard thing we have, you know, it's hard to figure out. It's a challenge is basically, I think as Chase said, is nowadays I say 100 wind turbines. How do I think about correlation? Or computationally, how do I deal with this sort of operation problems? That is still quite open to us. But with one wind turbine, we can do it fairly easily. So now this class to finish, we'll just look at the cross correlation, which gives an idea of how to quantify, right, how related they are or how anti-related they are. Okay? So the cross correlation. So there's a cross correlation defined by cross correlation coefficient. Okay, so what does the cross correlation coefficient do? Okay. And so let's compute the following. Okay, to get to this coefficient, this is written as rho of xy. This is the cross coefficient, okay, rho of xy. And to compute this, we need to compute the following things. Okay, so this is saying given wx, wy. So we need to compute wx average, wy average. Okay, so these are the things we need to compute before we get to this number. We also need to compute sigma x, sigma y, right? So these are the standard deviations. Okay, these are the standard deviations for each of them individually. Okay, so let's compute all these sort of terms for each of these random variables individually. Then what we get to is we have the cross correlation coefficient is given by this somewhat fancy looking formula. Over the product of these two. Okay, so this is a fancy looking formula. You'll see this a lot because this is, you know, easy to write down. But we can expand this into a sum. So the sum for this thing is all the possibilities, the joint probability, okay, so if you have the table of probabilities, it's given by this equation. It's given by this equation. Right. So this, you know, just so given the joint probability, we're plugging into this equation, we can compute everything here and compute everything here. So, okay, so then the important thing is if you look at this, this is a number between -1 and 1. It turns out this number is bounded between -1 and 1. Okay. So being 1 means they're entirely correlated. They move in the exact same direction. One is large, the other one is at maximum, the other one is at their maximum. Being -1 means they're entirely moving in the different directions. Okay. One is large, the other one is small. Imagine moving in this kind of direction. Then if they're 0, means they're not correlated. What one does has nothing to do with what the other one does. Okay. So you have this sort of cross correlation. And this is a second order statistics, right? This is sort of a simple measure of how correlated they are. So often in practice, we have multiple turbines or multiple sites. We'll measure the cross correlation. We'll measure the cross correlation. Typically, you don't want them to be too correlated to each other. Things being too correlated creates basically issues because they can both be 0. So things are very correlated means they're likely to be both very small at the same time. And that can create a lot of challenges for us when we're operating the system. So often when you measure sites, you want to make sure that they're at least somewhat, they're not perfectly aligned. Right? At least they're not perfectly aligned to each other. Any questions about this cross correlation coefficient? Okay, so let's do one example for this, right? So let's do one example for this. Right, so for example, we can have two wind farms with the following measurements. Okay. So the way we did our measurement is we went and we took 5 measurements, and each time we measure, for wind farm 1, we get the first measurement, wind farm 1, we got 5 meters per second, wind farm 2, 2 meters per second, and so on. Okay, and we want to find the average, both the standard deviation, and let's say we want to find the cross correlation between these two sites. Right, so let's go find each of them. So let's find the average. Okay, let's find the average. So to find the average for a single site, you basically pretend the second one doesn't exist and just use the normal formula. Because here we're only looking at 1, right? The site 1 for average. Okay, so we can ignore the fact that we also measured wind farm 2. It doesn't enter into the average computation of wind site 1, wind farm 1. So this average is 1/5, 5 plus 0 plus 1 plus 6 plus 10. Right, so this is my average for the first one. This is 4.4. And then the average for the second one, again, we ignore the fact that we have an additional wind farm here. We'll simply add them up. Add this up, we get 3.7. Any question with this? Right, so here we're still computing individually for each of them, right? So we can ignore the other one. Okay, where we cannot ignore it is compute the cross correlation, but we haven't gotten there yet. Okay, we'll compute the cross correlation there. So this is the average. So now let's compute the standard deviation. So sigma 1 squared, this is 1/5. So this, I recall the formula is 1/n summation wi over w minus wi average squared. So here I have 1/5, 5 minus 4.4 squared plus 0 minus 4.4 squared. This whole thing, and sigma 1 is the square root of sigma 1's squared. So if you take the square root, we get 4.04. Okay. Now similarly for sigma 2, we get 3.23 meters per second. So these are the individual ones, these so-called sort of the marginal values. Then to compute the cross correlation, right? To compute the cross correlation, what we get is 1/5, sigma 1, sigma 2, then a big summation. And inside the terms we have as, to recall, this is our equation. So we have 5 minus 4.4 multiplied by 1 minus 3.7 plus 0 minus 4.4 multiplied by 3 minus 3.7. We add all the things up and we get something 0.77. Okay? So this is, both are fairly correlated. This is above 0 means they're correlated, and this is quite close to 1. So meaning they're, so when one is likely to be high, the other is also likely to be, one is likely to be large, the other is also likely to be large. So this is how we compute cross correlation, right? So often what we do is you go out in practice, you construct a table like this, right? Although a much, much larger table like than this one. And then you compute the cross correlation this way. And you want a good understanding of for this sort of farms, how correlated they are. Question about this?
Yeah, I had a question.
Yeah.
I'm not sure if you said this before, but if it's less than 0, do you call that anti-correlated? I know you said if it's greater than 0.
Yeah, so less than 0 is anti-correlated.
Okay, what is 0 then? No correlation?
There is 0 correlation, no correlation.
Okay,
so
thank
one
you.
doesn't have much to do with the other one. Yeah.
That makes sense.
Yeah, so 0 doesn't quite mean they're independent in a statistical sense. But in practice, the most thing we measure to is cross correlation. So 0 will say they're not correlated. Okay, so again here, remember this is just correlation, right? So our correlation for wind energy, we're not talking about something like cause and effect, right? We're not using correlation in that sense. So we're using correlation strictly to mean this formula. Right? Just plug into this formula, compute the number, that number is called correlation. Gives the idea of how much they tend to move close. Right? They are how close, how aligned they are in their movement. Any other questions? Okay, so yeah, so if not, thanks. We'll end earlier today I need to talk to the ClickUp speaker. Right, so if you're not coming to the seminar on Tuesday morning, I encourage you to come. At least watch the videos. Right, so this quarter is all energy systems. So you hear some interesting talks that way. Okay, and you can ask to meet with the speakers actually. Over Zoom, it's not quite easy to talk to them. They're all willing to talk to students. If you see one talk that catches your eye, or after listening to a talk, you want to have an individual time with the speaker, just let me know. These people are quite open to meeting students. Okay, so other than that, thanks guys. I'll see you on Thursday.
Thank you.
Thank you.
Thank you.